So this is what we arrived at in the last lesson about the angular momentum when we have fixed axis rotation. That we have an orbital part and we have a spin part. Or in other words, we have angular momentum due to the motion of the center of mass of the object and an angular momentum due to the motion of the object around its center of mass. All right. If we are working with fixed axis rotation, if the axis of rotation is fixed, then you don't really need to be working with a vector and when worrying about this general expression, you can just take the z component and that should be fine. Okay. And the reason is because if the axis of rotation is fixed and then you have translational motion, so then all you have to worry about is the z component, and that's it. So I may write z component and this moment of inertia around the center of mass times omega, or
Excuse me, sir.
yes.
कैमरा फोकस पे नहीं है तो कुछ भी नजर नहीं आ रहा कि आप क्या लिख रहे हैं.
Sure.
अब सही है सर.
Is because probably I'm moving. That's why I think the focus is fine. When I move and the camera tries to refocus, that's why it loses focus for a moment, right? So this is all about the angular momentum. How about the torque? So you see this very important result that we did for angular momentum, that angular momentum of an object which is both translating and rotating, we can separate its angular momentum due to its translational motion of the whole object, or so the motion, translational motion of, or the motion of the center of mass, and the motion of the rest of the object around its center of mass. But now we have to answer the same question about the torque. Okay. And when you see the result, you may say, well, this looks trivial and we could have written that just without doing the steps that I'm going to do. But the difference, I'll explain what the difference is. All right. So let's say that we have, let's just consider an example to make it. Let's say that we have a disk and center of mass coordinate with respect to this stationary origin coordinate system A, let's say, is this is R, and then we take a point on this disk whose coordinate in this stationary coordinate system is R, and then in the center of frame the coordinate is R prime. All right. And then of course disk has mass, and let's see if we need any more. And let's say that the disk is moving with a velocity in this direction. Okay. V, I mean the V is here, V means the velocity of the center of mass, right? So using this equation here, okay, or this equation, I can write L for such a system is R cross P plus this thing, the angular momentum in the center of mass frame of reference would be sum over R I cross Mi Vi prime. Okay. Now to calculate the torque, let's take derivative of the angular momentum. And remember, this angular momentum, this L total, is defined or is measured from this stationary origin, from a stationary frame of reference, a perfectly inertial frame of reference, right? You take this derivative and then you get dr cross P plus R cross dP over dt plus dt and everything inside the sum. Remember, these are coordinates with respect to the center of mass frame, right? Now, let's look at these quantities. What is this?
So ये velocity into momentum हो जाएगा.
जी?
तो खाली सर ये हो जाएगा ना velocity into momentum, तो the velocity तो ये हो जाएगा ना mv square, I think.
But it's a cross product between velocity and p.
फिर जीरो हो जाएगा.
Zero हो जाएगा because velocity is in the same direction as the momentum, right? So this term is zero. ठीक है? How about this term? What is this dP over dt?
Force.
That's force. Okay. So the relationship simplifies to R cross F plus dt and whatever in the brackets upstairs. Okay. Get it? This is dl over dt. All right. Now this is torque, right? By definition, as measured from this stationary frame of reference. Okay. This origin outside the object, torque. Okay. Now let me write another definition of torque. I'll just do it here. So if I'm writing the torque of this object, all right, then the torque is simply tau Ri, and remember this coordinate is with respect to this origin. Okay. Cross F. All right. And now if I substitute Ri, if I want to write Ri in terms of capital R and R prime, so can I do that? Right. And that would be simply R prime plus R cross F. All right. And this then simplifies to R cross F. Make sense? Is this transparent? Starting here by definition of the torque, and then we get to this expression. Okay. And then you look at this quantity here, which we calculate from by taking the time derivative of the angular momentum. And if you equate the both of them, then this term just cancels on both sides. This term here and this term here. ठीक है? Is it all too clear or not clear at all? Nobody is asking any question.
बता सकते हैं which term cancels out?
लेकिन ये टॉर्क है, हमने एक इनर्शियल फ्रेम में मेजर किया है, ठीक है, क्योंकि हम and we have used the angular momentum of in an inertial frame. L इसका टाइम डेरिवेटिव लिया है, so we get r times f plus टाइम डेरिवेटिव दिस टर्म होल हियर, नीचे नहीं लिखा मैंने दोबारा, ठीक है, ये जीरो हो गया, तो we get torque by taking the time derivative of the angular momentum, ठीक है, and then we have calculated the torque by using the definition of torque. Sum over the position vectors of all the particles or objects masses in this object cross or times cross product with force. And then I've changed the coordinates of r from this. I mean, I have not changed any coordinates. I've just written ri, the vector ri, in terms of r prime and the center of mass coordinate system. So sorry, center of mass coordinate. So that becomes ri prime plus r. And if I simplify this, so I get this expression for the torque. Now, if I equate this torque with this torque, you see this r cross f term is the same in both sides. So that cancels on both sides. And what I get is this. R cross F equals d over dt times, there is sum here, mi vi both primed. All right. Now, if I can just write this in more simpler symbols, this is torque in the center of mass is equal to dt over d over dt of L in the center of mass. Okay, it's very important. Okay. What I'm saying is that the torque of the torque in the center of mass frame of an object which is moving along which is rotating and translating with a fixed axis is equal to the rate of change of angular momentum in the center of mass frame. And this is not a foregone conclusion, because if we tried to calculate directly, we would have made a mistake. We could have made a mistake because the center of mass could be accelerating. But now the results we have obtained, we have used the inertial frame, and we have used the angular momentum measured from inertial frame and the torque measured in inertial frame. But then what we get is the result is that the torque in the center of mass of such a system is equal to the time rate of change of the angular momentum in the center of mass. Okay. And this is more or less it. So the scheme of things for solving problems, and we would solve one and see many examples in the recitation as well, is, so whenever now we have problems, we use F is equal to, so whenever we have whenever we have a problem where we have translational motion and rotational motion around fixed axis, and that is all that we would be doing in this course. So we use F equal to dp over dt for the center of mass motion, which is equal to ma, where a is the acceleration of the center of mass. Okay, so this gives us the translational motion, and for the rotational motion, then we use only the z component of the torque, which is equal to ICM alpha. And if we know the torque and if we know the moment of inertia, we can find acceleration. So this is basically the two equations that we need to solve whenever we are looking at an object's translation and rotation.
Excuse me, sir.
जी,
हम ट्रांसलेशन मोशन के लिए अगर फोर्स यूज कर सकते हैं तो हम रोटेशनल मोशन के लिए मतलब सेंट्रीपिटल फोर्स नहीं यूज कर सकते.
नहीं, वो फोर्स जो भी यूज हो रही है that is part of the torque, but I mean centripetal force, I mean the
because वो भी रोटेशनल मतलब रोटेशनल फोर्स ही होती है ना, जब कोई चीज रोटेट करती है तभी that force is produced, it's moving in a circular path.
You have to be careful with the centripetal and centrifugal force. I think you're referring to the fictitious force that we obtain and in some text, and otherwise
square over r वाली मैं उसकी बात कर रही हूँ, in case I get the name wrong.
yes, that's a non-inertial that's a non-inertial force. Now you have to be, yeah, so let's see, you'll see the example and you see that this is not related to that. Okay, all right.
So,
okay, now starts the more interesting bit. Okay, so have all of you seen a ball, have all of you been ever to, or have you been to a bowling alley?
yes.
If you have not, I'm sure you would have seen one in the movies. Okay, a bowling alley is where you have a big bowling ball that you throw into a channel or a track, and then if you're careful enough and good at it, it rolls down and then it hits a set of white pins, and then if you manage to strike all of them down, that you have done really well. That's basically the game, right? A bowling ball. So if you throw a bowling ball, and this is both a common observation and you can what happens is that when you throw a bowling ball on the track like this, it initially skids, but then after some time it stops skidding and it starts rolling only. Okay, and let's say we want to find out that, and in that's not the only question that we would be answering, it's a more interesting problem. But let's say we want to find out when does the ball stops skidding and starts rolling only. So the moment you throw the ball, okay, let's say that this is the ball and this is the track beneath it. All right, and when you throw it, it is skidding, so it is sliding. Okay, and it's also rolling. Okay, even if it initially is not rolling when you throw it because you're holding it in hand and it's not rolling, but the moment you throw it in the track, it starts rolling. Okay, after some time t, or let's call it t roll, after some time down the track, it stops skidding. Okay, and it is only rolling. Right, that is what is called, the problem is called rolling without skidding or rolling without sliding. Okay, and we want to find out what is that time, when would this ball would stop skidding and start rolling. Okay, let's start with a free body diagram. Okay, what are the forces? Weight downwards, right? Then there is, since there is no motion in the horizontal direction, normal force upwards. Let's not write it here. Let's just make free body diagram here. Weight downwards and normal force upwards. Any other force?
So frictional force को हम करेंगे consider.
Frictional force, yes, the friction force, since it is skidding rightwards, and let's say that we are given that the center of motion, sorry, the center of mass of this ball is moving initially. So that's when we throw it, the whole ball has this much v naught velocity in this direction rightwards. Let's call this ex direction. Okay, and this is ey. Okay, and since it is skidding in this direction, there would be a force of friction in this direction. Okay, so 3 forces in total. Anything else? All right, so if we know all the forces, is minus mg ey, and normal force would be, we don't know, we'll have to find out. So, and the force of friction, then if we know the normal force would be minus mu n ex in the negative direction. All right, so we write the equation for the y direction, and then that's sum of all forces, weight plus normal force, and there is no acceleration in that direction. So normal force is minus plus mg ey. All right, so that's normal force, and now we can figure out what the friction is. What is the friction then? Minus mu mg ex. Okay, all clear? Right, and now if we look at the x coordinate, then again solving, f is equal to ma, sum of all the forces, and since we are in the x direction, don't need to write vectors. So then acceleration, so then the force of friction mu mg is equal to ma. So what is acceleration then? What is acceleration?
minus mu g आ जाएगी.
A is equal to minus mu g. And do you get it why A is minus?
So backwards net force है, so it's trying to basically stop the ball.
Is decelerating, right?
Yes.
Because the object is decelerating. That's why acceleration is negative. So
Sir,
what would
friction में won't it be ex ey?
G?
Friction में हम ex ey नहीं लिखेंगे sir?
क्यों?
Sir, because n के साथ ey लिखा हुआ था, तो जब हम n को substitute करेंगे.
Oh, अच्छा. So you have to be careful. Friction की definition ये है कि only the magnitude of normal force.
Oh, okay. Thank you.
अगर वेक्टर फॉर्म में फ्रिक्शन n डालेंगे ना, तो फिर देखिए ना वो वेक्टर नहीं कर सकते, क्योंकि अगर वेक्टर फॉर्म में n डालेंगे तो फिर फ्रिक्शन इस डायरेक्शन में आ जाएगी. ठीक है, और अगर नेगेटिव साइन के साथ डालेंगे तो इस डायरेक्शन में आ जाएगी, जबकि फ्रिक्शन तो मोशन को अपोज करती है. तो वो फ्रिक्शन की डेफिनेशन में शायद ये क्लियर नहीं है कि इट्स द मैग्नीट्यूड ऑफ नॉर्मल फोर्स टाइम्स the coefficient of friction that gives you the magnitude of the force of friction, and direction you have to deduce from the motion. Okay, and we we are given that the object is initially moving with v naught in this direction. ठीक है? So we have to consider the direction of the frictional motion opposite to that. ठीक है?
Okay, thank you, sir.
All right. So how about then? Now we just calculated that the acceleration and by the way, this is the acceleration of the center of mass. Okay, if I didn't say it or if it wasn't already obvious, this is what it means. It's acceleration of the center of mass. Okay, which is there is no force rightwards because the track is flat. All right, and there is only one force that is acting and in the horizontal direction, and that is force of friction. So the object is slowing down. The center of mass of the ball is slowing down. Okay, and it's slowing down constantly. So what would be its velocity at time t if in the beginning its initial velocity is v naught? What would be its velocity at vt?
Minus mu gt.
At, and that means v naught minus mu gt. Very good, right? And it also gives you, as the time goes, as the time grows, as it gets longer and longer, the more we wait, this term grows, right? And at some point this would be equal to v naught, and what happens to vt? That it becomes 0. So this was a translational motion of the center of mass of the object. Remember, we just said that we have to consider both of the things. We have to consider the rotational motion, and we see that the object starts rolling at some point. And at some point it stops skidding and only starts rolling. So now we consider the torque due to all the forces that are acting on this object. So what forces are acting on this object? On the ball? Weight, normal force, and the force of friction. Okay, what is torque due to the normal force?
Sir, weight and normal force cancel out नहीं हो जाएगा since there is no मतलब vertical acceleration.
Now you can't cancel forces while calculating torque. Be careful with that. Okay, and let me give you an example. If you have an object of finite size, right, and you're pulling on this object in this direction, and if you're pulling on this object here in this direction with equal forces, okay, the same force F and the same force F, so wouldn't the object rotate?
It would, I think. हाँ,
It would
करेगा.
rotate. So if it rotates, that means torque is not 0, although the forces are opposite and equal. They are not
Correct.
collinear.
मतलब ये तब तो कैंसिल आउट हो जाता ना कि अगर आपकी जो बॉल है वो मतलब हॉरिजॉन्टली मूव ही नहीं करी. इसके अंदर हमारी जो बॉल है वो वर्टिकली मूव नहीं करी, इस वजह से मैंने कहा था कि नॉर्मल फोर्स और वेट कैंसिल आउट
देखिए,
हो जाता है.
but that's for the center of mass is not vertically moving. I'm asking now the torque due to these forces, the torque due to normal force. You have to be careful.
Okay.
देखिए ना, अब ये ऑब्जेक्ट बेशक कहीं मूव नहीं कर रहा, एक्सिस फिक्स है, it would still rotate even if it is not moving.
अपने वो पॉइंट पे रोटेट करता रहेगा इस तरह, अगर मतलब it's not moving for front.
Yes.
Back की तरह.
So that's why we have already considered the translational motion, and we have considered that there is no velocity or acceleration in the horizontal direction of the center of mass. Fine, but now we have to consider rotational part, but we don't need to invent the forces. We still need to work the forces that we have. Okay, so now we want to calculate the torque acting on this ball due to all these forces. So what is torque due to normal force? What is the definition of torque? let's say that the
So
radius
F
of the
cross
ball
P
is
ना,
r. Huh?
F cross R होता है ना, तो since R is in the same direction as दोनों vectors R और N and R or W in the same direction में, तो वो zero हो जाएगी ना torque due to the
Excellent.
vertical forces.
Yes, very good. That's the answer. Okay, that the two ways of looking at it. One is that the force is passing through, is exerting along the line passing through the center of mass. Okay, whenever that is the case, the torque is zero. Or you can think of like this, that the R is actually, for example, in this direction, and N is in this direction, and R cross N, since both are in the same direction, would be zero. So the torque due to the normal force would be zero. Okay, and then the torque due to the weight for the same reasons would be zero. All right. So how about the torque due to friction?
होगा सर बिल्कुल.
R
कितना
cross
होगा
F हो जाएगा सर.
जी?
R cross F के F
हाँ जी.
cross R.
R cross F होता है, F cross R होता है. Doesn't really matter though.
So would
Like
it
R
matter?
cross F. Yes, it would matter if you are not careful with the signs. Okay, it should be R cross F, and then R is they are making 90-degree angle. Okay, this is R, and they make 90 degrees. So R and F, and then what is F? We did calculate, right? F is the force of friction is minus mu mg, right? Mu mg. And the magnitude is negative. That indicates that since the motion is clockwise, and for clockwise motion, what is the direction of the torque? Into the plane, right?
Yes sir, into the plane.
ठीक है, that indicates that is where you get the minus R mu mg. That is,
आप प्लीज समझा सकते हैं कि मतलब हमें उसकी क्लॉकवाइज हो या एंटी क्लॉकवाइज उससे किस तरह
ये दोबारा पूछें, क्या पूछा आपने? क्या मुझे सवाल नहीं समझ आया. All right, so for the rotate, जी.
सॉरी, लेकिन जब आप वो समझा रहे थे कि एंटी क्लॉकवाइज जब होगा तो मेरा वो मतलब इंटरनेट रुक गया था, तो मुझे कुछ आवाज नहीं आई. कैन यू प्लीज एक्सप्लेन अगेन?
ठीक है, देखें ये हमेशा ये clockwise anti-clockwise confuses. Look back. This is the quantity we are calculating. Torque F, okay, and is equal to R cross F. ठीक है, तो आप मुझे ये बताएं ना कि जो क्रॉस प्रोडक्ट है टू वेक्टर्स की, उनका रिजल्टेंट की डायरेक्शन क्या होती है?
सर उनके रिजल्टेंट की डायरेक्शन वो होती है ना कि आर को आप बेसिकली रखते हो अपनी यू कीप द फिंगर्स ऑफ योर राइट हैंड इन द डायरेक्शन ऑफ आर एंड देन कर्ल योर फिंगर्स इन द डायरेक्शन ऑफ एफ, तो उससे आ जाता है हमारे पास. आई थिंक
बिल्कुल ठीक है, या दूसरे लफ्जों में, सादा लफ्जों में ये भी है कि these two vectors live in the same plane. Okay, you can always have, if you have two vectors, you can always find a plane that they live in. Okay, and then usually this vector is orthogonal to, makes a 90-degree angle with the plane of these two vectors. ठीक है, so if you consider this board as our plane, because that is where R lives and that is where F lives, right? Now how many choices do you have? How many possible vectors you can make which make a 90-degree with the board? Two vectors, one going out of it and one going into it, right?
बिल्कुल.
ठीक है, तो क्रॉस प्रोडक्ट का मतलब ये है कि अगर वो राइट हैंड रूल फिर लगाएंगे तो नेगेटिव का मतलब है कि इज गोइंग इनटू द प्लेन, एंड Positive ka matlab as going out of the plane. Okay. And then if the force is in this direction and R is in this direction, that is clockwise motion. Okay. So the torque would be into the plane of the board, and that's why its sign is negative, because the way we plot the x-axis, the coordinate system, usually is like this: x, y, and z. Okay. Z is considered to be, or sorry, that would be wrong. X, y, and z. Okay. So the positive z is when you have x towards right, y upwards, then the positive z has to come out of the plane of the board. So that is why if the torque is pointing into the plane, its sign would be negative. If it is outside, sign would be positive. And it pertains to two types of motion. If the motion is clockwise, it is into the plane of the board. If the motion is anti-clockwise, it is outside of the plane of the board.
Okay, thank you.
So now the torque due to the friction force, and that is the total torque actually, because all other forces are contributing zero torque, is equal to Fr. But then we know that torque by definition is ICM alpha. Okay. So equate both of them, where ICM is the center of, if the moment of inertia of a sphere around its center of mass. Did we calculate that in the recitation? Hmm? 2/5 mr square. Right? And then if you equate these two equations, you get ICM alpha equals FR, and then alpha simply becomes mu mg, okay, R over I. Okay? So that is the angular acceleration.
So हम I के अंदर 2/5 mr square values डाल के मतलब cancel out नहीं करेंगे whatever values.
हाँ कर सकते हैं, but let's keep it that way for a minute, okay? कर भी सकते हैं, ठीक है? Now let's find out the angular velocity. क्या formula है angular velocity का? At time t. Come on.
Sir, omega naught plus alpha t.
Yes, very good. Omega naught plus alpha t. Okay. Now imagine when the ball is in your hand and you're about to release it. You are giving it some linear momentum. You're giving it some initial velocity in that direction. But is it spinning? Is it rolling? No.
No.
So omega naught is initially 0 and omega t is simply alpha t. And now we know what alpha is, right? So then we get omega t equals, अब alpha की value डाल दें तो mu mg r over ICM times t. This equation here and this equation here, very important. So this equation is saying that the object is slowing down and at some time t, it would stop. Okay.
Okay.
And this equation is saying that the object would at some time t, as the time goes by, it would keep spinning faster and faster. Okay. Have you seen ever anything like that in real life?
सिर्फ स्नोबॉल होता है as it मतलब goes तो वो ज़्यादा speed उसकी increase हो जाती है I think.
किसकी?
जो snowball नहीं होता जो snow से बना होता है.
Probably it's because it's gathering mass, right? That's why the phrase snowballing.
Yeah.
And I say
Sir,
also
friction
it
का
also has
negative.
it also has inclination, but here we have a flat surface, all right?
Hmm.
And we're saying that one equation is saying that the object translation motion is going to zero. It's going to come to rest, its center of mass. This equation is telling us that it is going to be spinning faster and faster. Now the two, how do you reconcile? Have you ever seen a bowling ball after some time that it stops and keeps spinning?
Sir, friction का negative sign क्यों नहीं हमने लिया alpha में?
फ्रिक्शन का नेगेटिव साइन क्यों नहीं लिया हमने? कहाँ पे?
Sir, alpha के अंदर.
I was just calculating magnitudes and because both torques are negative, so you can also think of that. देखिए ना, ये वाला torque भी negative है और ये वाला torque भी negative है. Both are pointing in the z
Okay.
direction. We're just taking the magnitudes, right?
Okay. Thank you, sir.
ठीक है. So what does that mean?
So in जो equation है omega t की इसमें everything is मतलब it would remain a constant as we would move on. तो सिवाय time के तो can we say कि time increase हो रहा है इस वजह से omega t की value increase हो रही है कि बाकी सब कुछ constant रहना चाहिए along the motion in a straight line at least.
हाँ बिल्कुल ठीक है.
Okay.
So what is happening in reality is, as we do this experiment, that once we throw the ball, initially it's not rotating. Okay? Its rotation is zero, as we have taken omega naught to be zero. And now let's say if there was no friction, what would be the omega t?
0 जगह सर.
Zero. It would be zero. So what would be then vt?
सर V नॉट हो जाएगा.
V naught हो जाएगा. So if there was no friction, there would be no rolling. It's very, very important. There was no friction, there would be no rolling, and the object would continue its translational motion unopposed. It would maintain the speed.
Sorry.
All right. But if we include the friction, what happens is that initially we only have in the very beginning, when time is zero, we only have translational motion. Okay. And the object is skidding. Okay. But then friction, thanks to friction, it causes the object to roll as well. And then it plays another role. It slows down the translational motion of the center of mass. Okay. And it increases the rotational, the rolling of the ball. And when this velocity goes to zero, Vt, that is when the ball stops skidding. It does not stop translating in the absolute sense. Okay? It does not come to rest. It is just that it stops skidding. Okay, and it's only rolling.
Excuse me, sir.
Yes.
आपने कहा कि जब फ्रिक्शन नहीं होगी तो रोटेशनल मोशन नहीं होगा और सिर्फ ट्रांसलेशन मोशन होगा, है ना?
जी.
तो कोई ऐसी सिचुएशन होती है जिसमें ट्रांसलेशन मोशन नहीं होता लेकिन सिर्फ रोटेशनल मोशन होता है?
जिसमें ट्रांसलेशन मोशन नहीं होता, सिर्फ रोटेशनल मोशन होता है.
ठीक है.
Yes, exactly. That's what I'm trying to say. That after some time t, when these two terms become equal, there would be no translational motion.
सर लेकिन इसके अंदर इनिशियली तो होता है ना, मैं कह रही हूँ कि उस पूरे सिस्टम में किसी भी पॉइंट के ऊपर ट्रांसलेशन मोशन हो ही ना, सिर्फ रोटेशन हो. जैसे इस केस के अंदर व्हेन फ्रिक्शन इज जीरो, एट एनी पॉइंट ऑफ टाइम रोटेशनल मोशन जीरो ही रहेगा. समझ रहे? दैट्स व्हाट आई एम ट्राइंग टू से.
But that's a trivial case. Anything fixed to somewhere and then you keep rotating. There are countless examples of that. But there is nothing interesting about them. I mean, we have considered those examples, but this is more interesting because what I'm trying to lead this whole discussion to is that how translational motion and rotational motion are interconnected.
So
Okay. Can we have the discussion on the most important topic a bit later with more focus? But what does that mean? That when the translational motion is zero, then we have pure rolling. Okay, let's make that point more concretely. Okay. Let's say that a point on the sphere travels from an initial position to a new position, making an angle d theta at the center. Okay. So how much distance it has covered? L, right? And L is equal to, what is L equal to if the radius is R?
RD theta.
RD theta. All right. And then can I also write this R omega dt?
ये सब वही आ जाता है.
सही है. So this is the distance an object, sorry, a point on the surface of the sphere has traveled. Okay. In the meanwhile, if this object, its center of mass is moving with velocity v towards right, how much distance the center of mass has traveled?
V delta t.
into t.
Yes. So let's call this S. S is v into delta t. And this is the mathematical condition for moving without skidding when this distance that a point on the surface of this object or sphere travels the same distance as the center of mass of the translating object. Okay. When these two distances, when S is equal to L, or in other words, V dt is equal to R omega dt, when this is the case, that is a mathematical condition when the object is rolling without skidding. Okay. दूसरे लफ्जों में आप यूं भी सोच सकते हैं, more simpler. Okay. Let's say that this point goes a full rotation. ठीक है, goes a full rotation. तो कितना distance cover किया point on the sphere?
2 pi r.
2 pi r. If in that time If there is no skidding, then the center of mass of the wheel, if it's a wheel or a ball, would have moved how much?
2 pi r.
2
2
pi
pi
r.
r. 2 pi. But if there was skidding, then there would be additional motion. Okay. Skidding in either way. I mean, the skidding doesn't have to be, I mean, it could be, the distance could be larger or can be smaller.
सर अगर स्किडिंग हो रही होगी तो 2 पाई आर के अंदर एडिशनल v डेल्टा t हो जाएगा जो स्किडिंग वाली वैल्यू थी.
I don't know. You'll have to work that out.
Sir, they
But-
cancel out to give v is equals to r omega.
Yes. So this cancels out. And what we get is v is equal to r omega. Okay. Now what is r omega?
So ये तो centripetal velocity होती है ना, या angular velocity है.
V is the velocity of this point, the tangential velocity of this point around the center. Okay. यही है ना? ठीक है. That is r omega. And v is the velocity of the center of mass. Okay. When the velocity of the center of mass becomes equal to r omega, that is when we do not have skidding. In other words, the rotational motion and the translational motion are no more independent. They've been coupled. Okay. The translational velocity now depends on the rotational velocity.
So हम ये assume कर सकते हैं कि when we reach this point तो जो part मतलब जो भी हमारे पास object है उसका हर atom is moving at the same speed, क्योंकि इसमें outer atom भी इसी speed पे जा रहा है जितना जो center of mass वाला point है वो भी उतनी speed पे जा रहा है.
नहीं, बिल्कुल भी नहीं, because we are still rolling.
तो सर लेकिन इसके अंदर तो सेम मैंने देखा center of mass की भी speed v और जो outer edge के ऊपर atom या point है उसकी भी speed r omega equals to v ही है. So aren't they both moving at the same speed?
Yes, but in different directions. The speed is ये इधर को जा रहा है और center of mass
लेकिन
इधर को जा रहा है.
मैं बात करूँ ना magnitude की बात करी.
हाँ, magnitudes, yes. But then do not try to relate them in any way because center of mass is moving rightwards. Okay. Sorry,
Right.
this is incorrect. So and this is moving downwards. Okay. At some point, this point would be moving in this direction with r omega, and the center of mass would be moving in that direction. So this tangential velocity has all kinds of directions. Okay. The magnitude of the center of mass and the point at the edge become equal. But let me emphasize, this is the velocity of the center of mass. Okay. The velocity of the center of mass. So what happens to, let's say, now let's look at the translational velocity of the point of contact. POC. What is the translational velocity of the point of contact with respect to the ground or with respect to the track?
सर पॉइंट ऑफ कांटेक्ट तो सेंटर ऑफ मास के साथ नहीं आ गया कि वो करेगा.
नहीं, क्योंकि देखिए इट्स रोलिंग. ठीक है. And let me give you this example. Let me give you. If there is no rotation and there is only skidding. Okay, if there is no rotation, yes, then point of contact velocity would be the same as the center of mass velocity. Object ऐसे ही move कर रहा है, drag कर रहा है. ठीक है. If the object is both skidding and rotating, then जो point of contact की velocity है with respect to ground, ठीक है, that would be equal to v minus r omega. ठीक है, towards right, it is skidding, and then now it's consistent because if omega is 0, then the point of contact velocity is the same as the center of mass. Okay, if omega is not 0, then their difference gives you the point of contact velocity. And now you see the condition for skidding tells us the center of mass velocity is equal to r omega. So then what is the point of contact velocity?
0.
0. And if the point of contact's velocity with respect to the ground is 0, what about the force of friction?
0.
It becomes 0. Because so this is when you stop skidding and purely rolling, the friction disappears, or at least the sliding friction disappears. And that is why you see the two reasons here. Without friction, we would not have rolling. Okay, so thanks to friction, that helps us not skid and roll. Okay, and when we purely roll, when the motion is purely rolling, then there is no friction. Little surprise that cars are are moving on tires, wheels, not on square boxes. Okay, because rolling, although the absolute friction is never 0, and even if you have a rolling object, after some time it stops because there are other mechanisms involved and there is a rolling friction. But you see, one can argue that the rolling friction compared to the sliding friction is much less. Okay, that is why we have wheels with on cars, not boxes.
So can you explain कि आपको ये कैसे पता चला कि rolling की जो friction होती है it's very small, मतलब less than skidding की friction?
Because in ideal conditions is 0.
So ideal
It is
condition के
calculated.
अंदर skidding की भी तो 0 हो सकती है ना?
जी,
Ideal condition में skidding की 0 नहीं हो सकती friction.
so दोबारा कहें?
मैं कह रही हूँ ideal condition के अंदर skidding की friction 0 नहीं हो सकती.
अगर skidding की friction 0 होगी तो rolling ही नहीं होगी. Then you won't get the rolling friction to be 0. You would not get the rolling at all. Then
Right.
you would have skidding. ठीक है ना? So the skidding friction is helping us go from skidding to rolling. Skidding, the friction, the sliding friction helps us go from sliding, it stops sliding and it encourages rolling. That is the whole point of this lesson. Okay, it induces rolling. Once we go to rolling, there is no relative motion between the point of contact and the surface. And remember, what is the condition for friction? That the two surfaces should be moving relative to each other. And the two surfaces are not moving relative to each other. It is just that a new point comes into contact. A new point, as the wheel rolls on or the ball rolls on, a new point comes into contact. Okay, this is the picture. And if it was skidding, then what would happen is that every time a new point comes into contact, it also slides a bit. Then the next point comes in and slides a bit and slides a bit before it goes out of contact. Okay, that is rolling with skidding. When we have pure rolling, this object, once a new point comes into contact with the surface, it just stays there, then it goes out of contact on the other end. And then the object keeps rolling, keep falling. All right. So thanks to rolling that we get a very good efficiency out of machines.
Sir, can you please explain how we got that the velocity of the point of contact is equals to velocity of center of mass minus r omega?
Yes. So because at the point of contact, what is the velocity of the point of contact? Radial velocity. It's moving in this direction, right? Tangentially with r omega. Okay. And the center of mass of this object, if there was no rolling, so think of this, if there was no rolling, then this velocity and this velocity would be the same in the rightwards. The point of contact would be moving rightwards with the same velocity, that is vcm. But now, since we have rolling and the rolling motion is in this fashion, that this point is moving in this direction, and the difference of these two velocities gives me the net point of contact velocity with respect to this surface in this direction.
Sir, I don't understand it.
Mm. देखें, अगर ये व्हील है और आपने इसको जैम किया हुआ है, ठीक है, आपने इसको जैम किया हुआ है, एंड देन यू आर ड्रैगिंग इट, ठीक है, ये इसके सेंटर ऑफ मास की वेलोसिटी है, ECM, एंड द व्हील इज जैम्ड, इज ओनली स्लाइडिंग, तो इस पॉइंट की वेलोसिटी राइटवर्ड्स कितनी होगी? Is a jammed
It will
wheel.
also be VCM.
It would be VCM. ठीक है. But now you allow the moment you lift you take your foot off the brake pedal, तो क्या होगा? It would immediately move this way, this words, right? This point. ऐसे ही है ना?
Yes. Yes.
Right? So it would immediately move this towards this direction. So it has another velocity in this direction, which is r omega. Let's say that is the rotational frequency of this wheel. Okay. But it's not totally free to go. I mean, it's tethered to the center of mass. It's a rigid object. Okay. So now it's net, let's say that it is still not completely rolling, but still skidding and rolling. Then the difference of these two velocities, okay, v minus this one VCM minus this motion due to the rolling in this direction would give me the point of contact's net velocity with respect to ground.
Okay. I get it now. Thank you, sir.
Okay. And one more thing. The center of mass, when we have pure rolling, the center of mass velocity is not zero. Okay, is equal to r omega. That means the object is still translating. Only the point of contact velocity is zero. VPOC is zero. Okay? It means it's no more skidding, but it's still rolling.
सर
And
हमने
this
जो
is
न्यूटन सेकंड इक्वेशन से जो v निकाला था पहले, वो किस चीज की वेलोसिटी है?
वो सेंटर ऑफ मास की है. वो सेंटर ऑफ मास की है. ये
तो
सेंटर ऑफ
फिर सर
मास की.
वो वाली अगर सेंटर ऑफ मास 0 है तो फिर ये VCM r ओमेगा के
जी
सर
आपकी
वो
स्क्रीन स्टक हो गई है.
सॉरी क्या?
सर अगर वो VCM r ओमेगा के बराबर है तो फिर ये VCM 0 है, तो फिर ये किस तरह आ रहा है?
नहीं, मैंने VCM 0 तो नहीं कहा है. ये तो द पॉइंट ऑफ कांटेक्ट की वेलोसिटी 0 है. Okay, so there is no skidding. That is what this equation is telling us. Okay, and that is the condition
Yes, sir.
for the center of mass. That is the velocity of the center of mass when you would have no skidding. Okay, if the velocity is larger than r omega, then you are skidding. If the velocity is less than r omega, then you are skidding. Okay, and that is precisely what happens is when v minus r omega is greater than 0. Okay, that is what happens when you apply brakes. Right, when you apply brakes to the car, okay, you break this equation, because before brakes, this is what is established between the center of mass of the wheels, or the car, in other words, is exactly equal to the rotational velocity, the tangential velocity of the wheels. Okay, once you apply brakes, you reduce r omega. Okay, v remains the same, so your v becomes larger than r omega, and what you get is forward skid in the forward direction. Okay, and then now with the more modern cars, you have the ABS brakes, and the skid is dangerous because it can turn the car upside down. Is basically that's what the ABS brakes are doing. They are looking at the velocity, the speed of the car, and the rotational speed of the tires. And whenever they notice that this equation has been broken, they make the brake lighter, so that this equation comes into play again, and you don't have skidding. Okay, you keep applying the instantaneous friction force to slow down the vehicle, but you don't let the car skid. The anti-lock braking systems. Another example of another application of this analysis is that's how the bowlers swing the cricket ball, actually, because they roughen up one side of the ball and shine the other side. That creates different frictional forces on two sides of the ball. Okay, and then when you adjust the seam of the ball, you can control how much force you want on which side of the ball, and then you have different forces, and then control actually when you want to do reverse swing or the normal swing. By adjusting the seam, you can control how much force you want on either side. Okay, so just the last bit, and that is finally we need to what we promised that we would calculate is the T roll. So when does actually at what time, if we know the initial velocity v naught, what time does the object start, the ball starts rolling? And that is when you equate the just this equation, v is equal to r omega, and now we know that the expression for v is v naught minus mu g t roll equals r omega is simply mu mg r squared over I times t, right? And from here, you can calculate t rolling as v naught over mu g 1 plus mr squared over I. And this is pretty general result. It's also true. It's not just true for spheres. It's also true for cylinders. Okay, as long as the surface is horizontal, and then you can get the T roll for different shapes of between shape and sphere. The difference would be just the moment of inertia. So if you introduce the moment of inertia of cylinder here, you would have the time at which the object would start rolling if you are given the coefficient of friction and the initial velocity. So let's say that we are doing it for a sphere whose moment of inertia is 2 by 5 mr square. If you simplify introducing those values, what you get is 2v naught over 7 mu g. All right. Now we have calculated T roll. Let's put it back into the velocity of the center of mass. Which is what? V naught minus mu g T roll, and V naught minus mu g and T roll is 2 V naught over mu g 7, and this cancels here, and this simplifies to 5/7 V naught. So this is 5/7, and this is quite interesting. You see, that does not matter how heavy the ball is or the amount of friction that you have between the ball and the track. Whenever the velocity of the ball reaches 5/7 of V naught, the initial velocity, it would stop skidding and would start rolling. And interestingly, this value does not depend on mass, does not depend on anything else other than the initial velocity. And it does not depend on mu. Well, the only condition is that mu has to be greater than 0. If the mu is 0, if the force of friction is initially 0, then we would not get rolling at all. So it has to be greater than 0 as long as the coefficient of friction is non-zero, so there is finite friction, you will always get rolling, and the velocity at which the rolling happens is 5/7 times the initial velocity. So it slows down, and once it gets to this value, that is exactly when it starts rolling. And there is an example of slender on an inclined plane. I'm not sure if we would do it in the next class or not. So feel free to have a look at your notes.